Okay, welcome back. Happy Monday. Today we are covering class number 20. 20 is more about factoring and products of binomials. The demo today will be quite short. But I do want to highlight one thing. In fact, I have highlighted one thing, and that's the due date for the homework for today. When I handed you the homework schedule on the first day of the semester, I had originally had tonight's homework due on Wednesday, but Wednesday is our quest, and I did not mean to assign homework due on the same day as the quest. So I've changed it on my calendar. You don't have an updated printout of this, but I've changed it in my math lab. Tonight's homework is due Friday, okay? All right, but the quest is coming up on Wednesday. This is our third of 5 quests. The quest is covering material from lessons 14 to 18. That is not including today. Today is 20. In fact, it's not including Fridays either. All right, so just 14 to 18. Basically the stuff since the test, and then going up until Wednesday's class last week. Again, you've got that practice problems packet. Look on the first page of that document for the chart, which tells you exactly which problems you should be working on, lessons 14 through 18. And again, I have made videos and posted them on YouTube of me solving every one of those practice problems. Questions on the schedule? Okay, so here we are at the top of page 150. In this lesson, we learned how to factor the difference of two squares and quadratic trinomials where a is not equal to 1. Now, it strikes me that I haven't mentioned that a business yet, I don't think. But last class, we spent time factoring things that look like that. A, B, and C are just numbers. So for example, x squared minus x minus 12. We have that whole 2 by 2 box method to factor this thing into the product of two things in parentheses. Yeah? And you'll get lots of practice with that today again too. But in every one of the problems we did last class, there was an invisible 1 in front of that x squared. But today, it won't necessarily be 1. It'll be different numbers. Okay, so here's our demo. We'll start by multiplying out a few products by using the box. So let's give this a shot. X plus 3 times x minus 3. So maybe we'll just do one with the box and then the rest we'll do using another technique. So go ahead and make a 2 by 2 box right there. And then fill in the 4 areas of those little rectangles inside the bigger box. Make sure you multiply the right things together. Okay, and so if we write this out, x squared minus 3x plus 3x plus minus 9, excuse me. And what happens to those two terms in the middle? Cancel. And so we're just left with x squared minus 9, okay? Equal to x squared minus 9. And it's quite unusual for those two terms to cancel. Normally when you multiply two binomials together, that's what these two original guys were right there. When you multiply two binomials together, you'll end up with a trinomial right here. You'll have some middle term with an x and a number in front of it. But in this particular case, those x's magically canceled. Let's try this one. We won't use the box for the rest here. 7 minus y times 7 plus y. We saw a couple of classes ago, the box is just a fancy way to say distribute everybody in the first parentheses times everybody in the second parentheses. Again, you may have seen that as called the lobster claw method in a previous class. So when we do the first guys multiplied, what do we get? 49. And then we'll do the outer ones, plus 7y. And then the inner ones, minus 7y. Look at that. And then the last, minus y squared. And again, the middle terms cancel, and so we're left with 49 minus y squared. And so trying to get at the heart of what's making those middle terms cancel, well, the things in the parentheses are exactly the same as each other, except one of them has a plus sign between the two terms and the other has a minus sign between the two terms. And anytime you have that particular pattern, those middle terms are going to cancel. We just got duplicates, except one plus and one minus. And so in this last one, all that's going to be left is this guy times this guy, and that guy times that guy, but the outers and the inners, which I haven't drawn up here, are just going to cancel. What are the outers when you multiply them? Negative 10xy, inners, plus 10xy, and they'll just disappear. So all we'll have left are the first terms multiplied, which gives us 4x squared. And then the last guy is multiplied. Negative 25y squared. It's important to have that negative, right? One of them is a plus 5y, the other is negative 5y. So negative 25y squared. Okay, so easy enough to multiply those two things through. You don't need to memorize like this shortcut that says, oh, magically the outers and inners cancel. But what I do want us to take away from this is how to go the other direction. Multiplying things is easy. Factoring things is hard. But if you happen to see this particular pattern, then we're going to have a magical formula that will help us factor very easily. So here's the pattern. This thing right here, let's take a step back. How many terms? 2, whereas most of the problems we did last class had 3. So that's first kind of giveaway that maybe it's this special kind of factoring formula. So 2 terms. What's in between the 2 terms in every one of our examples is a subtract, right? It's got to be a subtract. And then finally, we observe that this guy is a perfect square, right? It is x squared. And this guy is also a perfect square. It is what number squared? 3 squared. This is a perfect square. What is it? 7 squared. And then this is a perfect square. It is just y squared. This one's a little bit tougher, but what is this guy the square of? Ellen, what are you pointing to? Oh my goodness, what happened? Thank you. What is this the square of? 2x. What is this the square of? 5y. And you'll notice 2x and 5y are exactly the things that we started with originally. So putting it all together, we've got this new pattern. It is called the difference of 2 squares formula, so named because it is a difference, subtract, between 2 perfect squares, right? A squared minus b squared. And if you see that and you want to factor it, we've got this nifty little formula that says a plus b times a minus b. That's it. So let's try it on this x squared minus 64 equals 2 sets of parentheses. We're going to run through our check of the 3 things that make it this nifty little new formula. Is it, how many terms is it? 2. What's the symbol between those 2 terms? It's minus, subtraction. And is each of the 2 terms a perfect square? X squared is just x squared. 64 is a perfect square. What is it? 8 squared. So our nifty formula is in play. It says all you got to do is write the a and the b and the a and the b with 1 plus and 1 minus. Well, let's see. What is the a? The a was the guy that was squared in the first term. What is it? It's x, right? X and x. And when you start thinking about multiplying these together, there's your x squared. The b is the guy that was squared in the second term. What was that? 64 is really 8 squared. So it is an 8 and it is an 8. And if you multiply them, distributing, you get your 64 back. What about the signs? 1 plus, 1 minus, it's done. Okay, let's try part B. 100 minus a squared times b squared. Running through our 3-point checklist. How many terms? 2. That's like the first tip-off that you might be in this case. What's the symbol between? Minus, that's the second tip-off. Last thing is important too. We need both of the terms to be perfect squares. Is 100 a perfect square? It is, it's 10 squared. Is a squared b squared a perfect square? It is, it's ab times ab. So this formula is in play. Okay, 100 came from what times what? 10 times 10. A squared b squared came from what times what? AB times AB. AB, AB. And if we're using this difference of 2 squares formula, what are the signs in between? 1 plus, 1 minus. Doesn't matter what order you put. One place where folks sometimes go wrong, most of the time the x squared is the first thing you see, which means the x and the x is the first thing that you write. But that doesn't mean that the variable has to be the first thing that you write. And in this case, the 100 is the first guy I see, and so the tens need to go in the first spot. You got to keep things in the same order. If you had said this, say, okay, let's see, a squared, b squared, that's my variable. It has to go first as ab and ab. And then 100 came from 10 and 10. 1 plus and 1 minus. This is not right. If you multiply this thing through, you'll get this guy, but reversed. You'll get a squared b squared minus 100, which is not what we have, okay? So don't read into this that the variable always has to go first. What has to go first is whatever went first in the original problem. In this problem, the 100 is the first thing, 10 and 10 have to be the first things. Okay, next one, tiny bit tougher, part C, 3r squared minus 27. How many terms? 2. What's the symbol between? Minus. Are they perfect squares? Is 27 a perfect square? We're done. It's not our new formula. So sometimes you get 2 of those 3 questions answered in the way you're expecting, and then the last one throws everything off and you just can't use the formula. But our technique is always factor out the greatest common factor first, regardless of what other factoring techniques we have in our back pockets. What's the greatest common factor of these 2 terms? It's 3, so let's take that 3 out of both of those terms. 3 parentheses. What's left in the parentheses? Yeah, we've got r squared still, and then minus 9, and I think, Lindsay, what you said is going to come up in the next step in this problem. Okay, so we factored out the GCF, but we still have to look at the thing in the parentheses and decide if we can factor it further. And now we're going to run through our same decision process. How many terms? 2. What's the symbol between? Minus. Are the 2 terms perfect squares? Now they are. And so now our formula is in play again. Equals parentheses, parentheses. R squared came from what times what? R. 9 came from 3 and 3. Signs, plus and minus in either order. This is not the right answer. What did I do wrong? I forgot the 3, right? That 3 is just hanging out. All we did was factor what was in parentheses, and we did that correctly. But you got to copy. Remember, a lot of math is copying everything, making one small change. That's the answer there. We're going to go kind of out of order here. I want to jump to E first. X squared plus 9. How many terms? 2. Symbol between? Plus. Is that okay? It is not. As soon as you see that plus in between, it's not this difference of 2 squares. All right, CBF, is that all right? Cannot be factored. I think that's good. Did we use, maybe we used the word irreducible last class. There are a few kind of synonyms for this. You can't factor it, even though x squared is a perfect square and so is 9. Like, it's tempting. I'm going to give you the opportunity to be tempted on the next quest or test, not this one, but the one after. I'll give you stuff that it's got perfect squares all over the place, but if there's a plus in the middle, you can't do anything with it. And you might be tempted, like there's a really natural thing to try here. X squared came from x and x. 9 came from 3 and 3. Yeah, and we can't make 1 a negative in this case, right? Because if you do plus and minus, that's going to be negative 9. We can't do that. So what's a natural thing to try to make plus 9? Plus and plus. Okay, that's a plus 9. That works. What's the problem? This is going to be a full trinomial. If you do the outers and the inners, in all of the previous examples, those 2 terms canceled. But here, what do you get? 3x and another 3x, and it's 6x, and they don't cancel. And that's why it doesn't work. So I'll leave that up there and then put a big old slash through it. No good. Okay, let's try D, toughest one. X to the 4th minus 16. How many terms? 2, symbol between. Minus, are they both perfect squares? They are. So we'll start with our two sets of parentheses, there and there. X to the fourth came from what times what? X squared times x squared. Got to be two copies of the same thing. X squared there, x squared there. 16 came from 4 and 4. Symbols between, plus and minus. So far, so good. We factored. But you always have to see if you can factor further. We have new stuff in the parentheses, and if you can factor any of them, you have to. X squared plus 4. Is that our formula? What's the problem with x squared plus 4? It's a plus. And we just saw in part E, we can't do it with a plus. What about x squared minus 4? That one we can do. And so we have to go farther here. Okay, so I'll highlight in green this guy right here, and we're about to factor it right over here. Parentheses, parentheses. X squared minus 4, first terms. X and X, last terms. 2 and 2. Symbols, 1 plus, 1 minus. The green highlighted things are equal. What did I forget? X squared plus 4. Remember, lots of copying. And just make one small change. So that guy is completely factored. Questions on that? Okay, a couple of observations about using this difference of two squares formula, dots, can abbreviate it. Difference of two squares only applies when you have two terms separated by subtraction, each of which is a perfect square. Those were the three questions we asked ourselves over and over again. You cannot use the dots formula, difference of two squares, to factor a sum, like in part E. No good. Sometimes you have to use dots formula twice on the same expression, like in part D. X to the fourth minus 16. We could use the difference of squares formula, but then one of the new factors could be, we could use that formula again. Any questions on difference of two squares? Okay, so to summarize, so this is the last factoring technique we'll have for the whole semester. So I just want to make sure we're clear on all the different techniques we have. First technique is the first one to try on every factoring problem, and that's factoring out the greatest common factor. Like in part C, what did we take out of both terms? 3. That's always the first thing to try, no matter what. Factor out the greatest common factor. Then we had the 2x2 box method, which we saw last class. It's on the next page, but this whole thing here where we, where is it? Not there. This whole thing where we fill in the 2x2 box and we do the diagonal thing and we fill in the empties, like all that stuff from last class. That was our second method. It's the most complicated. Our third and final method is this difference of two squares formula. It's only 3 things. And it's really nice in that the first guy is always what you look for first, and then you ask yourself if either of the other 2 factoring methods we have applies. Okay, so last thing, here we are on page 151. One detail. Suppose that that you started with some problem and you ended up filling in the box like this, like we're trying to factor something. I'm not telling you what we started with. I'm just filling in the box already. And now we'll go ahead and write the stuff that goes on the outside of the box. So what's the greatest common factor of the first row? 3 and also x. Okay, that's fine. And then once we know the first row, everything else is fixed. So let's go right up here. We know 3x times whatever goes in that circle is supposed to be the minus 6x squared. So what goes in the circle? Negative 2x, that's fine. And that will go up there. 3x times that orange is supposed to give me the positive 9x. What goes in the circle? Not just 3, but plus 3 is good. And then finally, this circle down here, or we can't look at the 3x anymore. Look at the negative 2x times that purple is supposed to be the minus 24x. What is it? Plus 12. Sounds good. And then just to make sure everything is okay, we check the bottom right. Plus 3 times the plus 12, does it work? Yes, okay, so everything worked out here. And so if we're just writing in our factors, I've already got the parentheses in part B. So looking on the outside, we go 3x plus 12, and then across the top, negative 2x plus 3. And at this point, last class, we were just done. That was the end of the problem. It was factored. Anybody notice something about the 3x plus 12? Something we can do? We can pull a 3 out of it. And we have to. Like, the problems here are all involving factoring completely. Get it down, broken down as far as possible. And 3x plus 12 is not factored completely because there is a greatest common factor of those terms that's different from 1. So we have to go farther with this 3x plus 12. So we'd factor out the 3, and let's just write our final answer here. 3 comes out. What's left from the 3x plus 12? X plus 4 is good. And then what are we copying just as it is? Negative 2x plus 3. And that's it. That's our final answer. Okay, so when might this happen? This actually happens because we forget to check for the greatest common factor initially. It's always the first thing we should do, but if you forget to do it, you still have an opportunity to catch it at the end. But just putting out there that normally when you write your final answer from the outside of the box, you're done. But just one last thing to check, make sure that the greatest common factor is 1 for everything in the parentheses. Questions on that? Okay, so on the next page, we're not going to run through it, but if you need a refresher of what we did last class, you could just try this problem now. Like, consider this to be the first problem with the activity, but it's kind of guided just to remind you of how we factored with the 2x2 box. And then the activity proper starts on the next page. Okay. Again, I'm looking for you to use a box on at least half of the problems in the activity, even if you have some other technique from previous math class to factor these. So use a box on at least half of these, and make a note someplace that you'll see it, that you're going to use a box on at least half of the homework problems as well. Okay, raise a flag if I can help.